Hello class, welcome to day 22 of Coronachem, period 4. This is for the grade 12 class, AP. One of the questions I asked you to do for homework was the practice example on page 745. The question goes like this. The value for KSP for manganese 2 hydroxide is 1.6 times 10 to the negative 13. Calculate the molar solubility of manganese hydroxide in a solution that contains 0.02 molar sodium hydroxide. So let's write down the conditions of the problem. First of all, the KSP is equal to 1.6 times 10 to the negative 13, and the substance is manganese hydroxide. And also the hydroxide ion concentration is 0.020 molar. So we'll let the manganese concentration equal to X. And if we set up a nice table with the dissociation of the substance, it's a marginally soluble substance, so very little of it dissolves, but you get some. You can set up a nice table, and this part's not really important because that's a solid. So a certain amount X dissolves and a certain amount X will be present at equilibrium. For the hydroxide, the concentration is 0.20, and some amount of hydroxide is added by the dissolution of the manganese hydroxide, so that at equilibrium it's going to be this much, and is dictated by this equation. KSP is equal to manganese ion concentration times hydroxide ion concentration squared. So in this case it's going to be X times 0.020 plus 2X all squared. What we can say, and that was the hint I gave you to do the completion of this homework, is that this quantity, this 2X, because this is a very low solubility, this part 2X is going to be so small compared to 0.02 that you can essentially ignore it without harming the outcome of the calculation. So what you'll get is 1.6 times 10 to the negative 13 equals X times 0.02 all squared, which equals X times 4.0 times 10 to the negative 4. So in the end, X equals 1.6 times 10 to the negative 13 divided by 4.0 times 10 to the negative 4. You get a value of X that is 4.0 times 10 to the negative 10, which is in agreement with what the textbook says. But I want to show you what it looks like if you don't do the approximation, because it makes use of a potentially useful function on your calculator. You'll see that it doesn't actually produce any real difference in the final answer, but it's good to have this technique available on your calculator because one day it might come in handy. I'll keep it on the upper part of the board because I don't like writing all hunched over. I was going to use my new board, but the new board has to be affixed to a solid surface. It's got a sticky backing, and I want to do that when I get to the country with my parents, so I'm not going to risk ruining the sticky backing for just one lesson. So, do one more in the fridge. Now, if I hadn't done the approximation and I had left the original amount, the original equation, unedited, I would have the following setup. I would end up with KSP equals 1.6 times 10 to the negative 13, which equals x times 0.020 plus 2x all squared, and that equals x times 4x squared plus 0.04x plus 0.04x plus 4.0 times 10 to the negative 4, which equals 4x cubed plus 0.08x squared plus 4.0 times 10 to the negative 4x. All of that equals 1.6 times 10 to the negative 13. So I could rewrite that in descending order of x powers by transposing that over. I'm going to rewrite the whole thing, but you get the picture. This can be transposed over here. And what you can do is solve for that using the cubic equation function on your calculator. I'll show you what that looks like. So you turn your calculator on, press mode, and you're going to see equation, that's number 4, so press 4. And don't press quadratic, you press cubic equations, that's 3. And then you'll see that it gives rise to 4 possible entries, A, B, C, D, and those are the coefficients that appear in front of each one of these, x's in the cubic equation, and the last one, the D value, is the one that has no x to it. So if you write the equation in descending level of powers, you can get your calculator to solve it up to a power of x cubed. So A, you're going to write 4 and then enter. Then for B, you're going to write 0.08, enter. For C, you're going to write 4 exponent negative 4, enter. And then the last one is 1.6 exponent negative 13, enter. Calculates for a while, and then you get 3 possible answers. Except I think I may have, yeah, I entered. This should have been entered as a negative number because when it's transposed it becomes negative. So the cool thing about it is I can just go scroll through all of them and put a negative sign in front of that one. 1.6 exponent negative 13. And there, okay, recalculate. So you get 2 answers. The first one is 4.0000015 times 10 to the negative 10, which is what, it's almost identical to the answer I got the first time with the approximation. With the approximation, that 0.15 part is missing, so it's 4.0 times 10 to the negative 10. So you see, making the approximation does not harm the value of your final answer. It doesn't even appear in the sig figs by a long shot. But it's just still good to know how to use that function of your calculator. So the final answer for this is that x equals, I'm not going to bother writing the other one because it's a complex number. You see that it's negative and it's complex. So 4.000, 4 zeros, 15 times 10 to the negative 10. So that's your solubility of manganese dioxide, the molar solubility. And if you have to stick to sig figs, you're only allowed 2, so the final answer ends up being identical to the one that you did obtain by the approximation. Next thing I want to address is how some substances are more soluble as the pH increases or decreases. And there are examples of that being done in the textbook. They show how magnesium hydroxide increases solubility when you have higher concentrations of protons. That's why you can take magnesium hydroxide as an antacid it'll dissolve according to need. So also the solubility of, basically in a nutshell, the solubility of slightly soluble salts containing basic ions increases as the pH, as the H plus increases, or as the pH decreases. And they also mention an example of how this phenomenon can create sinkholes in places like Florida, where there's a lot of carbonate containing rock like limestone. If you have an increase of acidity of the rain or groundwater, it can actually eat holes into the underground limestone, which creates a network of caverns, and then once the water starts to flow, they widen out, and sometimes they collapse, and you get sinkholes with entire neighborhoods have been known to sink into the ground. You see a picture of that on page 747. So it's an example of the phenomenon of increased solubility when you lower the pH. Carbonate containing rocks like limestone begin to dissolve when they're exposed to acidic conditions like acid rain. And it mentions the formation of complex ions on page 749. It describes what are called amphoteric oxides, like for example the oxides of alkali metals like sodium oxide, potassium oxide. Those, when you put them in water, form basic solutions. That's where they get alkali metals from, and alkaline earth metals. Then they mention selective precipitation of ions. That's on page 754. Techniques for separating through selective precipitation, where you know the solubility of different substances and what you can add to selectively precipitate certain ions and leave other ones behind in solution, so that you can isolate whatever it is that you're looking for. And that brings you to the end of the chapter. Just to consolidate your understanding, I think you should practice a couple of problems tonight. Try 1741. It shows you a titration. And there's a couple ways you can approach the solving of this problem. One is to do the actual calculation the old-fashioned way. The other one is to set it up as though it were a buffer system. Let me see how the way I did it, just before I give you bad advice. 1741. It's actually a pretty long question. 1741 covers several pages. It's one problem, but it covers several pages to solve. I made a data table out of it. So it took me 1, 2, 3 pages to solve it. And if you can get through that without too much trouble, then to my way of thinking, it shows that you understand this chapter. So try 1741 tonight, and let's see how far you can get. I'll just show you what pages look like, and you can always come back and look at the video. That's my answer key. So 1741. You can freeze it on the page that you need. Hopefully you can read that. And there's the other page. And then the last bit of the calculation. 1741 D, E, and F, I think. The last bit is up here. Okay, so try 1741. It's one problem for tonight. Hopefully, if everything goes well, by tomorrow I'll be in Apple Hill. Teach you from there. Okay, have a good night. Bye-bye.